Hello students, welcome to EPG Pathshala. I am Dr. Ravi Majumdar, Emeritus Professor, Department of Natural Sciences at West Bengal University of Technology in Kolkata, and formerly I was Professor and Head Biophysics Division, Saha Institute of Nuclear Physics in Kolkata. Today I am going to talk about the need for quantum theory and the Bohr model of atom. Well, the paper is Quantum Biophysics. Well, as an introduction, I would like to mention that the planetary motion about the sun is based on Newton's laws. Well, the same is the case for satellites, which goes around the Earth. Well, a planet or a satellite can take up any orbit around the sun. It can move around any orbit around the sun. All orbits are allowed. But in the case of an atom, for example, hydrogen atom, the electrons can only take up only a set of specific orbits. It cannot just take up any orbits like a satellite around the Earth. Now, since each orbit defines an energy level for the electron, only a set of discrete energy levels is allowed for the electrons. And the second point to note is that the electrons in these orbits, these allowed orbits, well, these are accelerated towards the center. And we know, according to classical laws of physics, that any accelerated particle emits radiation. But the important thing to note is that these orbits, these electronic orbits in atoms, these are radiationless. That is, as long as the electrons are in these allowed orbits, they don't radiation. And this gives stability to the atom, because if the electrons radiated, it would lose energy and fall back into the nucleus, and the atom would not be stable. So this is a very important point to note, that the electrons do not radiate in these stationary orbits, as it is called, or the allowed orbits of the atoms. Now, the Bohr model is really the starting point of quantum theory. So for the first time, it succeeded in calculating the discrete energy levels in a hydrogen atom. It could also sort of predict the wavelengths of light causing transitions from one allowed orbit to another. As I said, the electrons can take up only specific orbits, but you see, if you sort of subject the atom to radiation, then the electrons can absorb a given wavelength and jump from one orbit to another. And this sort of gives rise to what is known as hydrogen spectrum. So there are a series of lines which occur in the hydrogen spectrum, like the Balmer series, which is in the visible region, and also there are other series which are observed outside the visible regions. So previously one didn't really understand, you see, what are these lines, Balmer lines. But now we know that according to Bohr's theory, the Balmer series or any other series corresponds to electron jump from one orbit to another. Now, the objectives of this lecture is to understand the need for quantum theory and to learn Bohr model and the discrete energy levels in atoms, and to sort of understand the Balmer series in the visible region of the hydrogen spectrum, and also analyze the other series in hydrogen atom, and finally to identify the existence of atomic shells. Now, students, before we proceed further, well, let us see the photographs of Newton and Kepler. Well, these are the very two important people who developed classical physics. As you know, Newton has his laws of motion, and the entire classical physics is based on Newton laws, and Kepler applied these laws to study the motion of planets around the sun. Well, in this slide, we see the pictures of two other scientists who are pioneers in the development of the model for atoms. One is Rutherford, who first discovered that the nucleus of the atom is confined to a very small region and the electrons are outside the nucleus. And we now know that the electrons move in different orbits. And the other picture is of Niels Bohr, whose theory we are going to discuss in the coming slides. Before passing on to the Bohr model, we must be clear about the role of quantum mechanics in biophysics. Why do we need quantum mechanics in biophysics, and what is really quantum biophysics? Why do you call it quantum biophysics? Now, after the discovery of DNA double helical structure, which is known as Watson-Crick model, the key role of modern biology is to find the structure of proteins and other molecules that regulate the gene and keep our cells alive. Now, once the problem is reduced to the study of molecular structures, biophysics plays a crucial role. In long chain molecules, for example, their folding pattern depends on how the electronic charges are distributed in the molecules. We really call it electron charge densities. So this involves the study of quantum mechanics. And finally, the Bohr model of atoms is the starting point. It only describes the energy levels in atoms, but our aim is to study the electronic and other transitions in molecules, which involve, all kinds of transitions: electronic, vibrational, rotational, and also the folding of molecules. So for this, we need to solve Schrödinger equation, which is called modern quantum theory based on wave nature of electrons. So we'll come to these in our next lectures. Right now, I would like to just mention that quantum mechanics is an essential component of our PG Pathshala course. In this slide, we are sort of going to discuss Bohr's theory or the Bohr model for hydrogen atom. Now, it's a known fact that the electron's angular momentum, in an atom, let us say, is the cross product of two vectors, that is the radius vector and the momentum vector. So L is equal to R cross P, which is equal to M times R cross V. V is also a vector, that's the velocity vector, and these are clearly shown in the picture that the vector, in the case of a circular atom, the vector V is perpendicular to the vector R. That is, in a circular atom, the velocity of the electron at any point is always perpendicular to the radius vector. This is the characteristic of motion of a particle in circle, and therefore, as we have seen in the last line, it is mvr sine theta, that is the magnitude of the angular momentum, and since theta is 90 degree, the velocity being perpendicular to the radius, so theta is 90 degree, and therefore the angular momentum, its magnitude, becomes equal to mvr. So this is the result to note, that you see the angular momentum of the electron when it moves in a circle is equal to the mass of the electron multiplied by its speed multiplied by the radius of the circle. So L equal to mvr. What is Bohr model? So in Bohr model, there are basically two equations. The first equation, as you can see, is really the classical equation for circular motion of electron in a hydrogen atom. So we write mv squared by r, which is the centripetal force, and that should be equated to the electrostatic force. That is Ze squared by r square, and k is the Coulomb constant, because we are measuring everything in mks units. So if you compare this equation to the motion of Earth around the Sun, there mv squared by r is equal to the gravitational attractive force. But here, in the case of an electron, mv squared by r, the centripetal force, is equal to the electrostatic force of attraction between the electron and the proton. So this equation tells you that the kinetic energy, which is p squared by m, that's the kinetic energy of the electron, that is equal to k ze squared by 2r. So this is the first point in Bohr's model. And here there's nothing new. It's just like the equation you write in a classical theory. Now the second point is the most important point. So this is called Bohr's postulate. So the first equation has to be combined with Bohr's postulate. And what is Bohr's postulate? Well, it tells you that the orbiting electron's angular momentum are quantized, as it is called. That is, we have, in the previous slide, we have learned that mvr is the angular momentum of the electron. So that must be an integral multiple of h by 2 pi, where h is the Planck's constant. And it is usual to denote h by 2 pi, you see, by h cross. So we really write mvr, the angular momentum of the electron, is equal to an integral multiple of h cross. And what is the value of h cross? Well, it is h by 2 pi, and it turns out to be about 10 to the power minus 34 joules second. So this equation tells you that the momentum of the electron is restricted to only discrete values, which is n h cross by r. Getting p, that is the momentum, by last two equations, I mean those in the previous slides, if we eliminate the momentum, then we get an equation for the radius of the electronic orbit in the atom, and the radius is equal to n square h cross square divided by kzme square, which can be written as n squared times a, where a is the radius of the first orbit, and which is h cross square by kme square. So this radius a, well, that is the radius of the hydrogen atom in the ground state, or the radius of the electron in the ground state of the hydrogen atom. And this radius is a very important length, and this is called the Bohr radius. That is the radius of the electronic orbit in the ground state. And this defines really the size of the hydrogen atom. This is about half an angstrom unit, or 0.05 nanometer. So it is important to note from the first of these equations that the radius of an orbit is proportional to n square. Well, if the radius of the first orbit is a, then the second orbit should be 4a, and the radius of the third orbit should be 9a, and then it should be 16a, like that. So these are the allowed radius of electrons in a hydrogen atom. That is the radius of the ground electron in the ground state and the various excited states. Now, the question is, what is the total energy of an electron in an orbit of radius r? Well, the total energy is not only the kinetic energy, because the electron is not a free electron, it's a part of the hydrogen atom, and therefore it has a potential energy also, and that is actually the Coulomb potential energy. So the kinetic energy is p squared by 2m, and plus the potential energy, and the potential energy is given by z squared by r with a minus sign, because this is an attractive potential, and it's multiplied by k. And the kinetic energy was calculated in the beginning, which was k z squared by 2r. So finally we get the energy equal to the sum of kinetic and potential energies, and it turns out to be minus z squared by r multiplied by the Coulomb constant k. So we find here that the energy of an electron in the bound state is negative. Now, why is it negative? Because the potential energy sort of outshines the kinetic energy, right? The potential energy, which is negative, is twice the kinetic energy in magnitude, and therefore the net energy of an electron in the bound state of the hydrogen atom becomes minus kz squared by 2r. It's negative. So we have found out the expression for the energy level, which contains the radius. And we have already seen that the radius is quantized. That is, there can only be fixed radii in the hydrogen atom. So if we plug in the expression for the fixed radii or the allowed radii in the expression for the energy, then we find that the energy levels becomes quantized. As you can see in the screen, the energy level is inversely proportional to n square, where n is an integer. So this integer, well, these are positive integers, 1, 2, 3, 4. Well, this positive integer n is called a quantum number. And if you're talking about the hydrogen atom, then the atomic number Z has to be set equal to 1. So these are really the energy levels of the hydrogen atom. Well, if you put Z equal to 1, Z is the atomic number, you should remember. Well, here on the screen, you can see a very useful working formula that the energy levels of an atom is minus 13.6 Z square by n square, and the unit is electron volts. Well, Z is the atomic number, so for a hydrogen atom, you put Z equal to 1. So you find that the ground state energy of an hydrogen atom is minus 13.6 electron volts, and the higher excited states will have n equal to 2, 3, 4, and so on. If you take the first excited states, you have to put n equal to 2, and you get the result in electron volts. Now, what is an electron volt? An electron volt is the unit of energy when you come to atoms and molecules. So we know that in the world of atoms and molecules, 1 meter is a very big unit. So the length is measured in angstrom unit or in nanometer. Now, what is 1 nanometer? 1 nanometer is equal to 10 to the power minus 9 meter. So similarly, well, if you measure in joules, it's very large for in the atomic and molecular scale. So you use an energy which is 1 electron volt, and that is equal to 1.6 times 10 to the power minus joule. And as I have already explained, that the bound state of an electron in an atom is always negative. Well, as I have already told you, that the energy varies inversely as n square. So energy of the first 3 excited states are 4, 9, and 16 times less in magnitude than the ground state energy. So as a result, the excited energy levels get closer and closer together as we go to higher and higher energies. So according to Bohr, these orbits are radiationless. That is, as I have already mentioned, that the electrons do not radiate in these orbits, and that's how the atoms are stable. But, well, if you subject the atom to radiation, the electron jumps from one orbit to another. That is, the electron is capable of changing orbits. Well, it can take only fixed orbits, but it can absorb radiation and jump from one orbit to another. So this results in the observed hydrogen spectrum. That's the hydrogen spectrum is due to the transition of electrons from one orbit to another. So now we come to the hydrogen spectrum, and the spectrum which is observed in the visible region is called Balmer series, and it was observed way back in 1885. It was observed by Balmer, who was a school teacher in Switzerland. Well, he was sort of playing with the various lines which occur in the visible region of the absorption spectrum of hydrogen atom, and he found that there are certain wavelengths which are missing, and the wavelengths of these missing lines could be calculated by what is known as Rydberg's formula. This is purely an empirical formula which you can see on the screen, and R is called the Rydberg constant, which you can also see on the screen. So the missing wavelengths were obtained by putting n equal to 3, 4, 5, 6, and so on, and this is the Balmer series. Well, on the screen you can see the Rydberg formula once again, but this time the Rydberg constant is given in terms of the atomic constants like the mass of the electron, charge of the electron, and Planck's constant, and so on. And the question is, how do you obtain this formula from Bohr's model? So what you do is you calculate the energies of the level n equal to 2 and any other level n. So you calculate the energy gap, you see, by subtracting the energy of one level from the other level. You see, that's the energy gap, delta E, and you equate that to h nu or hc by lambda. So that's the way you can get lambda, or in this formula as it is shown, 1 by lambda, which is equal to rz square times 1 by 2 square minus 1 by n square. And you straight away get the value of the Rydberg constant in terms of the atomic parameters. And this really is in full agreement with Rydberg's formula, and this also confirms Bohr model. Well, it says that the Bohr's model is correct. At room temperature, the transitions take place from ground state to the excited states. Okay, and the series of missing wavelengths for these transitions lie in the ultraviolet region. This is called Lyman series. Now, for heavier elements like molybdenum or tungsten, the spectrum shifts to the X-ray region because 1 by lambda is proportional to z square, and so you find that for heavier elements, the spectrum shifts to the X-ray region. See, but so other observed series also lie outside the visible region. For example, Paschen series lies in the infrared region of the hydrogen spectrum. Now, the reverse transition gives the emission spectrum consisting of bright lines at the same places. Now, I must remind you that Balmer series, you see, occurs in the visible region of the spectrum, but in order to observe the spectrum, you have to heat the atom to higher temperatures so that the first excited state n equal to 2 is sufficiently populated. Only in that case you will see Balmer series, which lies in the visible region. But you see the Lyman series, see, it occurs, see, for hydrogen atoms in the ground state, but you see the Lyman series occurs in the ultraviolet region. So now on the screen you can really see the emission spectrum in the visible region. That is, in other words, the Balmer series for the hydrogen atom. So you can very clearly see these lines. The red line corresponds to, these are the emission lines, as I said, and the red line corresponds to the transition from n equal to 3 to n equal to 2, and the next one, you see, that is from n equal to 4 to n equal to 2, and the next one on the left, that is more towards the blue region, that is the blue line, and then the violet line. So the corresponding transitions or the electron jumps are shown below the spectrum. Now in the screen you can see the same picture which you just saw, that is the emission lines of the hydrogen spectrum in Balmer series. That is the picture on the top, and the picture on the bottom shows the corresponding absorption lines which occur in the same region, as I have already told you. So here this is a pictorial representation of the transitions which occur in Balmer series in the visible region, and Lyman series in the UV region, and the Paschen series in the infrared region, IR region. Okay, so the Balmer series occur in the visible region, and so they are shown in colored with sort of colored lines. But as I said, that you see, these are transitions to the first excited level, which is n equal to 2, and you have to heat the atom, you see, to get the Balmer lines. You can see them from the lights coming from stars, you see, because the hydrogen gas in stars, they are at higher temperatures. So if you analyze those, the light coming from the stars, you can see all these series, okay, which correspond to different temperatures. Now let us discuss a few points about elliptical orbits and the existence of shell in atoms. Now the atoms are actually three-dimensional spherical objects, and it has, both circular and elliptical orbits having different orientations in space, as in the planetary model. Well, according to Bohr's theory, Well, electrons can only move in circles, but in real practice, well, you can have elliptical orbits as well. And for this, you see, we sort of have to explain you see how the elliptical orbits, these both circular and elliptical orbits, how these are arranged in different types of shells like K, L, M shells and so on. Now, what are these shells? Now, the first orbit of the hydrogen atom, or the orbit in the ground state, electron in the ground state, well, has a circular orbit, and this orbit is also called K shell. In other words, the K shell of the atom consists of one circular orbit only, and according to Pauli exclusion principle, an orbit can accommodate a maximum of 2 electrons with opposite spins, which means that the K shell can accommodate only 2 electrons. Now, if we are considering the excited states of the atoms, then the next excited shell is L shell. Now, L shell actually consists of one circular orbit and 3 elliptical orbits, and these can accommodate a maximum number of 8 electrons. Now, atoms in biologically important molecules are mainly carbon, nitrogen, oxygen, and hydrogen. Well, these consist of 6, 7, 8, and 1 electrons respectively in the atomic ground states. So, all these electrons can be accommodated in K and L shells only. Now, the Bohr's theory applies to circular orbits only, but as I already said, that the atom consists not only of circular orbits, but circular and elliptical orbits. So the theory of elliptical orbits was developed by Sommerfeld, and this was an extension of the Bohr model. Now, since atom is really a three-dimensional object, so it can be described not really by one quantum number n, but there should be 3 quantum numbers, and those 3 quantum numbers are called L and M, which we'll see a little later. Now, n is then called the principal quantum numbers, and they define the shells like K, L, M, and so on. And for a given value of n, well, there is other quantum number L, which is called the azimuthal quantum numbers. And the azimuthal quantum numbers are restricted to values 0, 1, 2, 3, and so on up to n minus 1. So if you are considering, let us say, M shell, which is n equal to 3, then L, the azimuthal quantum number, can only be 0, 1, and 2. So, and you define these these values of the orbits with L equal to 0, 1, 2, 3, and so on by S, P, D orbits and so on. Okay, we have talked about the quantum numbers n, L, n, and the third one is the quantum number m. Well, now on the screen you can see what are the possible values the quantum number m can take. Okay, this for a given value of L, the magnetic quantum numbers, as they are called, well, can assume 2L plus 1 values, that as you can see in the screen. For example, if you have, let us say, a p orbit, which means L equal to 1, then m can have 3 values like minus 1, 0, and plus 1. And if you have a d orbit for which L is equal to 2, then you can have m equal to, say, minus 2, minus 1, 0, plus 1, and plus 2, like that. But you see, what I wanted to say is that here, these are sort of described by Sommerfeld, as I said, as an extension of Bohr's theory. But actually, these results, that is the idea of 3 quantum numbers that follow rigorously from the solution of Schrödinger equation in 3 dimensions, well, which we'll talk about after 2 or 3 lectures. Elliptic orbits and shells. It's very important, as I said, to define the shells on the basis of the quantum number n. So n equal to 1 is the K shell. I think I have told you about it. N equal to 2 is the L shell. So the K shell consists only of a 1s orbit, which is a circular orbit for Bohr's hydrogen atom. So if you talk about the quantum numbers n, l, m, this can be 1 because n is 1, then l can only be 0 and m also has to be 0. Okay, that's for the K shell, so it can accommodate 2 electrons. Okay, and then L shell is n equal to 2. So the various possibilities of n, l, m are shown on the screen, and so you see there are 4 possible orbits, and they correspond to 2s orbit, which is a circular orbit, and there are 3 elliptical orbits, which are designated as 2px, 2py, and 2pz, because these are directed in 3 mutually perpendicular directions. In other words, these have different orientations in space. And then the next point is to note that the energy levels, you see, depend on the principal quantum number n only, as in the Bohr model. Okay, so for example, in L shell, all the 4 orbits, 2s and 3 2p orbits, have the same energy level, E2, which is calculated from the Bohr model by putting n equal to 2 in the expression for the energy levels. So these are called degenerate states, and we'll learn much more about these things when we talk about the Schrödinger equation in modern quantum theory. We just say a few more words about the elliptical orbits and shells. One thing which is important to remember is that the transitions are restricted by certain selection rules. For example, one of the selection rules is delta L equal to plus minus 1. You see, these are the only transitions which are allowed. You see, any transition for which delta L is different from plus minus 1 is not allowed. For example, the electron cannot jump from 2s orbit to 1s orbit. Well, this transition is forbidden. Why is it forbidden? Because, you see, delta L is equal to 0 for this transition, okay? Because s and, you see, because both are s orbits, okay, 2s and 1s, okay, so delta L is equal to 0. And this finds very important application in lasers. Well, that is, this 2s state is called a metastable state, well, because it cannot decay into a 2s state. See, that is forbidden by the selection rule. And the second thing is that the number of orbits in a given shell with quantum number L is n square, and therefore, since each orbit can accommodate 2 electrons by Pauli principle, the number of electrons in these shells can be 2n square. For example, K, L, and M shells can accommodate 2, 8, and 18 electrons respectively. Well, this forms the basis of periodic table of element. Well, regarding the selection rules, we'll come back to this again while talking about Schrödinger equation. Well, this shows the atomic orbits, circular and elliptical, in the case of carbon atom on the right, and you can see the shells on your left. You see for the same carbon atom. That is, you can see clearly that K shell can accommodate 2 electrons, and L shell can accommodate the remaining 4 electrons for a carbon atom, because the carbon atom has 6 electrons, so two of them in the K shell and the remaining 4 in the L shell, because the L shell can accommodate up to 8 electrons. Well, this again shows the various shells. K shell, which can accommodate 2 electrons, the L shell, which can accommodate 8 electrons, M shell can accommodate 18 electrons, N shell, which can accommodate 32 electrons. Well, as I have already told you, that the number of electrons is given by the formula 2n square. So these are the various energy levels in terms of shells. Well, here we have given the electronic configuration of the first 10 elements of the periodic table, starting from hydrogen, which has got only one electron, and the electronic configuration is written like this: 1s, and then on the top it is written 1. That is, it has got only one orbit, 1s orbit, which is a circular orbit, and there is one electron in that orbit. For helium, it is 1s2, because both the electrons can be accommodated in the 1s orbit. And then lithium, beryllium, and so on. And finally, neon is an inert gas, because both K and L shells are completely occupied. 2 electrons in the K shell, and the remaining 8 electrons are accommodated in the L shells, 2 of them in 2s orbit and 6 of them in the 3-2p orbits. Well, this is more or less the same picture as you saw a little while ago. There we had shown the electronic configurations, carbon, and then now you can see the electronic configuration of the first 20 elements, okay? How the electrons are arranged in the various shells for the first 20 elements of the periodic table, starting from hydrogen to calcium. Now you can see the last picture which I wanted to show on your screen, and this is a very important sort of picture. And I have already told you that if you have a heavy element like molybdenum, for which the atomic number is 42, or if you have tungsten, for which the atomic number is even more, well, in that case, lines in the Lyman series, they are sort of shifted more towards the X-ray region. And this is exactly what you can see from this picture, that you are having 2 lines here. When the molybdenum atom is bombarded by electrons, then you see the electrons are impinging on a molybdenum surface, and as a result, X-rays are emitted, and which you can see in the background. But in addition to the background X-ray distribution, you can see 2 peaks. One is K alpha and the other is K beta. Now, what are these peaks K alpha and K beta? Well, these result from the transition from the shell n equal to 2, that is from the L shell to K shell, that is n equal to 1 for K shell. And what is K beta line? Well, that is a transition from n equal to 3 to n equal to 1 shell, which means that is a transition from M shell to K shell. So these are sort of, this confirms Bohr model all the more. Okay, you can see the 2 lines in the X-ray region as expected for molybdenum. We have now come to the end of the lecture. So students, let us summarize, see what we have learned from this module. Firstly, we tried to analyze what is the need of quantum theory, and why do we particularly need quantum theory in biophysics. And we have discussed that the study of biophysics is basically the study of biologically important molecules, and that involves quantum mechanics. And secondly, we have learned about Bohr's model and how Bohr's model lead to discrete energy levels in atom. Actually, what is really Bohr model? If one asks this question, then I should say that it is basically the classical equation of motion, that if the electron goes round in a circular orbit, then the centripetal force has to be equated to the electrostatic force. So that is purely classical, and with that, Bohr added a postulate which is very fundamental, and that is called the Bohr's postulate, that in any given orbit, the angular momentum of the electron must be an integral multiple of the Planck's constant. So this is exactly where the quantum mechanics comes in, and this leads to the discrete energy levels of the atom, as we have seen. And then number 3, well, we could explain the Balmer series of the hydrogen spectrum on the basis of Bohr's theory of hydrogen atom. As you know that the Balmer series is the only series which appears in visible region, and we have seen that this corresponds to the jump of electrons from one orbit to another. Well, if you are talking about the emission spectrum, then Balmer series actually is the jumping of electron from the third shell to the second shell, or fourth shell to the second shell, or fifth shell to the second shell of the atom. And then we have some other series of the hydrogen atomic spectra. Well, those are Lyman series and Paschen series. Those are outside the visible region. Lyman series, for example, occurs in ultraviolet range, and Paschen series occurs in the infrared range. So these are the spectra in the invisible region of the atom. And then finally, we have learned about the elliptical orbits. Well, actually, we said that the atoms are actually spherical objects, so it has got circular and elliptical orbits along different directions, and these are arranged in shells. So we have learned about the atomic shells in different atoms, and we have also discussed how the electrons are arranged in different shells according to the periodic table.